Good day. In today's lesson, we'll be going through how to change higher order differential equations into a system of first ordinary differential equations, and we're going to go through this with two examples. So, our question says you are supposed to convert the following initial value problems into a system of ordinary differential equations, and this is our first ordinary differential equation with the IVP given, like the initial values given, and this is our second ordinary differential equation. So let us start with. So we start with our first example. So you realize that with our first example, our question is the cube y the t cube plus the y the t all squared plus 3y equals et. So you realize that our ordinary differential equation here is of the third order because of these three here. I hope you can see that. So we are supposed to reduce this into a system of first order differential equations, ordinary differential equations. So what we do is that we let y here be equal to a certain variable, let's say x1. So we will let the y dt be equal to say x2, and the squared y dt squared will be equal to x3. So when you are forming these equations, we always end at the n minus 1th order. So you realize that our question was of the third order. So when you are forming these equations, we are going to end at the second order. So we always end at the n minus 1th order. So when we get this equation, next thing we do is that we differentiate both sides of the equation. So when you differentiate both sides of this first equation, we'll get the y dt be equal to the x1 dt. With the second one, we are going to get the squared y dt squared be equal to the x2 dt. And with the third one, we are going to get the cube y dt cube will give us the x3 dt. Right. So realize that the x1 dt is equal to the y dt, but the y dt here is what, x2. So that means we have this to be our first system of ordinary differential equations. When you get to the second one, we have the x2 dt is equal to, so we can see is equal to the squared y dt squared, and the square y dt squared is equal to x3. So that means we have our x3 here. And the next one is the x3 dt is equal to the cube y dt cube. But note that in our question we had the cube y dt cube plus the y dt all squared plus 3y plus et. So to get the cube y dt cube here, that means you're supposed to make it the subject in our main question. So making it the subject, you're going to get the cube y dt cube will equal to et minus the y dt all squared minus 3y. And this is the same as et, but remember that the y dt is equal to x2. So that means you have x2 here, but it is squared, this squared. Then y is equal to x1. So we have 3x1. So that means in place of this, we're supposed to write, so we write et minus x2 squared minus 3x1. The last thing to do is to get our initial condition. So you realize that the initial condition given was y of 0 was equal to 1. But remember, y is the same as x1. So that means here we have x1 of 0 is equal to 1. The second initial condition was y prime of 0 was equal to 0. And know that y prime is the same as the y dt, and y prime is the same as x2. So that means we have x2 of 0 is equal to 0. The last initial condition was y prime prime of 0 equals 0. So meaning x3 of 0 equals 0. So this becomes our system of first order ordinary differential equations, which our third order differential equation has been reduced into. So that's the solution to the question. But just a quick one. Sometimes you can be asked to write your system of ordinary differential equations of the first order into a matrix form. So let's see how we go about it. So once again, recall that these were our systems. So the last one was, we have this was equal to 18 minus 3x1. And our initial condition was x3 of 0 equals 0. So remember, this was the system we had, and we realize that we have a non-homogeneous term here. So that means when you're writing this system of ordinary differential equations in the matrix form, you get something like this, where this is the non-homogeneous term. So when you're writing, you realize that we get our x dot. And know that our x dot is the same as the x1 dt, that's this vector, the x2 dt, and the x3 dt. So that's what our x dot stands for. Then we are going to get x dot will be equal to, we have x1 here, x2 here, and x3 here. Then we have our x1, x2, x3 here, and plus our non-homogeneous term. So you realize that when it comes to the first one, so you realize that the x1 dt is equal to x2. So that means that our x1 component is 0, this is 1, and this is 0. With the second one, this is 0, this is 0, and this is 1. When you come to the third one, we know this place is -3. But when you get here, you realize that we have a squared here. And this squared here makes this particular differential equation non-linear. And because our differential equation is non-linear, it means that we can't write it in a matrix form. So with this particular question, we can't write it in a matrix form. But if our question had happened in a way where these two wasn't there, if these two wasn't there, so note, if these two wasn't there, then we would have gotten -1, 0, and 0, 0, and our non-homogeneous term was et. To realize that this is the same as ax plus f of t. So x dot equals, as we said, remember that we only wrote this assuming that our s2 squared wasn't squared. So for this particular question, we couldn't have written it in a matrix form, but I ignored it when intentionally formed matrix for it because I wanted you to know how to form a matrix for it when the system of ordinary differential equations are linear. So let's solve the second example. So with the second example, it was 2y prime prime minus 5y prime plus y equals 0. The initial conditions were given as this. So, solution. We let y to be equal to x1 and the y dt to be equal to x2. Note that the y dt is the same as y prime. Note that we end here because our differential equation here is of the second order. So we end at the n minus 1 order. So the next thing to do is to differentiate both sides. When you differentiate both sides, we are going to get the y dt be equal to the x1 dt, and this will give us the squared y dt squared be equal to the x2 dt. But note that the x1 dt is equal to the y dt, and the y dt here is x2. And you realize that the x2 dt squared, oh sorry, dt is equal to the squared y dt squared. So to get this the squared y dt squared, that means from the question we are supposed to make y prime prime the subject. And the question was 2y prime prime minus 5y prime plus y equals 0. So to make y prime prime the subject, we are going to get y prime prime will be equal to 5 over 2 y prime minus y over 2. So this means you're going to get the x2 dt will be equal to 5y prime over 2 minus y over 2. But note that y prime, which is the y dt, is equal to x2. I hope you remember. Yeah. And we said our y was equal to x1. So this will be x1 over 2. So that means finally, we have our systems of ordinary linear equations as the x1 dt equals x2 with initial condition x1 of 3 equals 6, and we have the x2 dt equals 5 over 2 x2 minus x1 over 2 with x2 of 3 equals -1. I hope you know how we form the um, initial conditions here. So the question was y of 3 equals 6, but know that y is the same as x1. So here it was x1, and it was y prime of 3 was equals to -1. Y prime is the same as x2. That's why you saw the x2 here. So that means when you are done, we can write this into a matrix form. Writing it in the matrix, you realize that with this particular system of ordinary differential equation, we don't have any homogeneous term here, a non-homogeneous term here, sorry. So that means that our x dot will be equal to ax because this is equal to 0. So that means we just have ax. So in doing that, you're going to have x dot, or the first derivative of our x's will be equal to, so you see here our x1 component here is 0, we have 1 here, here it is minus half, and here it is 5 over 2, and we have x1 x2. So this is how to write our question in the matrix form. So this is it with changing higher order ordinary differential equations into a system of first order ordinary differential equations. Thank you.